titration particle model number 3. This time we are titrating a weak acid, acetic acid, and a strong base, sodium hydroxide. Now there's some things that jump out at me from the titration curve. I see the equivalence point. It's way up here, maybe just under 9. But that makes sense because the acid will not fully ionize and the base does. So even if I had a 1-to-1 mole ratio, just because of the tendency of the particles to ionize, it may not be 100% neutral. Slightly basic, that base fully dissociates. Now if I follow it down, I still see 60 milliliters. If I were to write an equation, let's say we wrote this kind of like the net ionics. So we'd have the hydrogen acetate, and it would react with the base. I'm going to put it in as hydroxide. I know that the sodium and hydroxide would come together, but the sodium is a spectator. The acid will donate its hydrogen to form some of the negative conjugate base and some water. And eventually I might want to do some ice tables. And I do see that it would react in a 1-to-1 ratio. And for whatever amount of acetic acid does dissociate, it'll give off 1 hydrogen that will neutralize 1 hydroxide. And so with it being a 1-to-1 ratio in the balanced equation, at the equivalence point, I'll have equal moles. I've got 60 milliliters of each solution, and they're both 0.1 molar solutions. It's just that the weak acid will not fully ionize and give up all its hydrogen, so it may not be fully neutral, even though we're at the equivalence point. Now, some really good things are going to come out of these particle models. First, we should probably count everything, right? Okay, so now to make this a little more manageable, is it okay if instead of like writing this giant formula, can I just call it HA? Would that be okay? And then instead of writing the acetate ion, I'll just call it A minus. Could you live with that? So that now if I'm counting in this first box, I see 6 sodium, and then I'll call it 6A minus, which would be the acetate ion. And then I've got 1, 2, 3 sodium. I've got 1, 2, 3 of the A minus and 3 HA. Here's all 6 HA, acetic acid. And then on the bottom, oh brother, 2, 4, 6, 8 sodium. 1, 2, 3, 4, 5, 6. We'll call it A minus. And looks like 2 hydroxide. That's fun. Then I got 2 sodium. 1, 2 A minus. And 1, 2, 3, 4 HA. And finally, and this is the easy part, right? I think I can count these guys. 1, 2, 3, 4. Well, that's a bad 4. I can do better. 4 sodium. 1, 2, 3, 4 A minus. And 1, 2 HA. Fantastic. All right, well, I bet we can pick out point A, right? At point A, I should have all my weak acid. Now, they are showing the weak acid as not at all ionized, which I guess, I mean, even if this only ionized by like 1%, 5%, if I only had 6 molecules, they'd probably be not ionized at all. So would we be okay labeling this guy as A? Just the original weak acid? I think that makes some sense, huh? Okay, so HA. Now, let's see what's going on. I'm going to jump around a little bit here. And I think I'm going to start with, the box on the middle bottom. Let's see what happens with this guy. All right, so if I set up a little ice table, and I see that there's 2 sodium. All right, well, that 2 sodium would have also meant that there was initially 2 hydroxide. So I'm going to put this in as 2 in the initial. Okay, now I see that after a reaction has occurred, there's 4 of the HA. So what if I put this in as 4 of the HA? And now technically, there's no hydroxide in this container. There's just the 2 sodium left over. I'm looking at this guy, bottom middle. So yeah, there's the 2 sodium, spectator, but that hydroxide is gone. So that must have been the limiting. So this would have gone down by 2 to be 0. So if I kind of backtrack, this would have gone down by 2 as well. Would it make sense that it would have started at 6? Or if I kind of think about like box A, that there were initially 6 of the HA. So that if that goes down by 2, I would have 4 left over. I'm calling it HA, but it really is like the acetic acid molecule. Ah, okay. So initially, I would have had the 6 acetic acid molecules and the 2 sodium hydroxide. Initially, I mean, before any reaction, there would not have been anything on the product side. But I'm shifting forward by 2. Oh, so this guy's going up by 2. Now, I called it A minus in my little diagrams. And yeah, we're going to form some water, but they're not showing water molecules. Okay, do you see how this kind of matches that box middle bottom? That once all is said and done, once I hit equilibrium, there would have been 4 of the acetic acid molecules left over. Initially, I had 6. There initially would have been 2 sodium hydroxide. That went down to 0. That was my limiting reactant. But the 2 sodium are still left over. And then if we shifted forward, we would have produced 2 of the A minus. There weren't any initially, but I produced some. Look what I just produced. I just made a buffer. I didn't start with a buffer. I started with some weak acid and strong base. Here's a trick question that comes up on the AP exam, where they might say, like, can this form a buffer? And we're so programmed to think that a buffer is weak acid, conjugate base. And it is. And often when we make a buffer, we start with a weak acid and its conjugate base. But we can also form a buffer in a situation like this, where I had weak acid and strong base. As long as the strong base is the limiting reactant, it'll go down to 0, and you'll produce the conjugate base. So even though I didn't initially have any acetate, I formed some acetate. That's still a buffer. It'll be relatively acidic because I've got more of the acetic acid than I do the conjugate base. This is like point B, where I start to mix the acid and the base. I form a buffer, but when I look at the concentrations, it still should be acidic. I've got more acid than I do conjugate base. Okay, I can do that. Look what happens in the top row middle box. Check this out. All right, so I'm going to kind of erase these guys, and let's play the numbers game again. So I'm going to this box now. Wow! Come back. I'm going to this box now. Okay, so there's 3 sodium, which must have meant that initially there were also 3 hydroxide. Initially there were 6 HA, or 6 acetic acid molecules. Initially, no products. So these guys react as completely as possible. This guy's my limiting reactant. The hydroxide is gone, down to 0. So there's no hydroxide in that box, top row, middle box. But there is the 3 sodium. They're just the spectators that are still left over. I'm going to bring this guy down to 3. And then, yep, we're going to form a buffer. I don't care about the water. But same thing as the last one, that even though I didn't start with a buffer, as a result of the reaction, I formed some of the conjugate base. I formed a buffer. And I just didn't form any buffer. I formed the special 1-to-1 ratio buffer. We formed that special buffer where you have a 1-to-1 ratio of the acid and the conjugate base. And do you remember that when we were using the Henderson-Hasselbalch equation, we said then that when your buffer has a 1-to-1 ratio, the pH equals the pKa. Because then this ends up being plus the log of 1, and the log of 1 is 0. So at this special point in the buffer where you have a 1-to-1 ratio, the pH will equal the opposite log of your Ka. This is another special point in the titration. And it's no accident, this is going to be point C, put a little C in there, that if you look at point C and you follow it down, it's 30 milliliters. So if point E is called our equivalence point, point C is called your halfway point. Or sometimes they'll call it the half equivalence point. It's exactly what it is. It's halfway to the equivalence point. And it's such a special point. So if I knew that the equivalence point was at 60 milliliters, if I take half of that, I'd be at point C, 30 milliliters. We'd be at the halfway point in the titration. And at the halfway point, I'm going to get something that looks like this, where I've added half as much base as acid. And what happens in your ice table? You get the special 1-to-1 buffer. If then you could take this point C and follow it across, let's say I get a pH of about 3. Well, if the pH is 3, you can say then that the pKa is 3. Or in other words, the Ka is 1.0 times 10 to the negative third. This is a way of identifying an unknown acid. If I can find the pH at the halfway point, which I can get off my graph now, I know that at the halfway point, it's the magical 1-to-1 ratio buffer, where if I take that pH and go 10 to the negative third in this case, that would help you identify the acid if it was an unknown acid. Oh my gosh, that's magical. I do feel like we should practice that. And we will. That's a really important point on the curve. The halfway point and the equivalence point are the two most important points on that titration curve. Okay, that's a lot. Let's keep going. Let's see if we can find point D. All right, let's see if I can find point D here. So point D, I'm wondering if it's going to be down here. I wonder if it'll be this guy. If I had 4 sodium, there would have been 4 initial hydroxide. There were always 6 of the original acid and no product. If these guys react as completely as possible, we're shifting by 4. So the hydroxide is gone. There's no hydroxide in this last box, but there's still the 4 sodium spectators. This guy's going down by 4 to 2. So yep, there's still 2 of the HA, 2 of the acetic acid molecules, and then we're going up and up. Technically, I don't care about the water, but I just formed a buffer again. No way. I just formed a buffer. I didn't start with the conjugate base, but I formed it as a result of the reaction between the original weak acid and the strong base. So the strong base is gone. The hydroxide is gone. In exchange, I formed a little bit more of the weak conjugate base. But I still have a buffer. But see how my ratio is now starting to become a little bit more basic? I mean, it's still going to be an acidic buffer, but the pH is starting to increase. This is point D. Of the 3 points, B was a buffer, C was a buffer, the special buffer, the 1-to-1 ratio buffer, and point D was a buffer. Those points fall at this part of the graph right in here. Where, yeah, I mean, I'm adding that strong base, but the pH really isn't changing all that much. That's because you're forming a buffer. And in fact, we call this the buffer region. Or sometimes we call it the buffer zone. It's that point at the bottom of the titration curve where you are adding hydroxide, but you're forming a buffer. So you don't see a pretty dramatic increase in the pH. Not until we hit the equivalence point. The equivalence point, what's that going to look like? Well, let's see if we can find the equivalence point. So we'll get rid of this buffer. So the equivalence point, I should have equal moles of hydrogen and hydroxide. I wonder if that's going to be this guy, point E. Let's see what would happen. If I had 6 sodium, there would have been 6 hydroxide, and there was always initially 6 of the original weak acid. Yep, here it is. Products are 0. This is my equivalence point, where I have equal moles of acid and base. But watch what happens. So these guys are going to react down to 0, and these guys are going to go up. Okay, so first thing I notice is that I do not have a buffer. Not a buffer. I lost all of my weak acid. So all I have is the conjugate base. Oh, that's why the pH is slightly basic. In a strong acid, strong base, all you're forming is water and totally neutral ions. Here, I don't have a buffer anymore. I lost my acid. That's why the pH changes pretty dramatically. And the pH is in the basic range, like maybe around a 9 or so. Because all I have left is the sodium ions, which are spectators. And I've got the acetate ion. And so basically, it is like a solution of sodium acetate. Yeah, you've got the conjugate base of a weak acid, which is a slightly basic solution. Fantastic. Now, by process of elimination, this must be point F. Now, watch what's happening now at point F. I am beyond the equivalence point, right? Okay, we're beyond the equivalence point. If there were 8 sodium, there would have been 8 hydroxide. If there would have been 6 of the original acid and no product, I think I see what's happening here. Yeah, I'm beyond the equivalence point where now my limiting reactant has become the acid. It's gone. And look what's in excess. I'm beyond the point where these two are equal. there's 2 excess hydroxide. These guys are still going up. 6 and 6. And so now look what happens. All that's left in the final solution is my 8 sodium total spectators. And I've got some strong base, and I've got some weak base, the conjugate base. Well, there's no doubt in my mind then that the final solution is pretty basic when I've gone beyond the equivalence point. So yeah, I'm looking at a pH of a little over 12. That's point F, when there's excess hydroxide. There's so much good chemistry in here. This particle stuff is really intense when you start breaking it down, huh? So you could try the last one. And obviously you could pull up the video and just let it play and listen if you'd like to. Or try the last one, and if you feel pretty good about it, just fast forward to the end and see if you're kind of getting it right.